lovely people, and I'm quoting one of my favorite YouTubers, Emma Thorne. If you like snarky takes on religion, check her out. She's pretty amazing, plus fantastic accent, right? So, anyways, that sidetrack aside, and I'm full of them tonight, we're going to talk about, we're skipping a whole bunch of material in the geology lectures, but we're going to look at chapter 18 in the old book I used. I know it doesn't make a lot of sense if you don't use the same custom textbook that the old university that I went to used. But glaciers and ice ages. And the reason I'm bumping this one up significantly in the order is because we're also going to talk about climate change. And that is an issue that is really quite big. Oh, you know what I should do? Anyways, it's an issue that's really big just in general, and we need to pay attention to it. Oh, there it is. Laugh at me, it's fine. So, there it is. Beautiful. Hello, lovely people. Starting over, right? I'm not going to edit the rest of that out because it's me, right? And if you were sitting in my classroom and I had started like that, I would continue like this. And I want to give you kind of an experience that's fairly authentic to having a professor that screws up sometimes. And even if they don't admit it, every professor, every instructor screws up occasionally. And I like to just keep it in there because I think it's funny and I think it's humanizing. So, onward, right? 2 waffles, maybe. If you're good. Everybody gets waffles. Everybody should have waffles. So, glaciers or glaciers and ice ages. We study glaciers a lot. Some people do. And some of the reasons for that is, obviously, if you live on the west side of the United States, and I mostly mean the west side of Washington State because that's where I live and that's where I typically teach. Glacial landscape is kind of everywhere, and even places that have not been impacted directly by glaciers have been impacted by these glacial floods. And we'll get back to those, but they're pretty amazing and also pretty significant. Another reason to be interested in glaciers is that many of our national parks, both in the US and in Canada, and any place around 45 degrees north or northern, it's going to be impacted by glaciers. And they tend to leave some really gorgeous landscaping and really striking landscaping behind them. And a lot of our parks have glaciers still on them or were created by them. Just think about that. See if you can name any. I mean, besides Glacier International Peace Park, or Glacier National Park if you're just in the US. But there are a lot that have been impacted by glaciers. And the other, and I think most important, conversation we're going to have in this entire presentation / video is the interconnection between glaciation, glaciers, and global warming. We'll get to why that is. It's a very large part, though. And it's really, really important, especially if you live in low-lying / coastal areas, because sea level, right? I mean, you know. Anyways, we'll get there. There we go. Okay. Had to make sure I hadn't skipped a slide. So this was probably 10 years ago that this article was issued, but it was kind of a big deal at the time because they recorded one of the Pine Island ice shelves calving, which is to say dropping a large berg or chunk of ice that was big. And an expert on the subject said that the land ice on that area is deeper than sea level. So if the whole thing were to drop into the ocean, we'd get a 3.3 meter or 9 to 10 foot rise. And if you think of the average person standing about 6 feet tall, and I am well under that, but so 6 feet's a good measure. You're talking 1.5 people deep in water. Yeah, can't live there. It's kind of a mess, right? So, bye-bye Florida, because Florida is really flat. And that's in part because Florida used to be, and when I get to geologic time, we'll talk about that, but it used to be part of an ocean. True story. So, what are glaciers? Or glaciers? It depends on how I feel like pronouncing it right. These are just large bodies of ice that are in motion. And they form from the accumulation and compaction of snow and ice. You need low temperatures, obviously, because ice doesn't form at high temperatures, right? So if it's like 30 degrees Celsius, it's going to melt. And I can't translate that directly into Fahrenheit off the top of my head. I just know it's really warm. So like 70, 80, 90, not 70, 70's chilly. Like 80, 90 degrees Fahrenheit, depending on your humidity, would be high temperatures, right? So way too hot for us versus, oh my God, it's cold, right? So we want it to be freezing to form glaciers. And these bad boys move under the influence of gravity, which, since we're skipping chapters you haven't heard me say 18,000 times, gravity drives a lot of everything on the planet. Gravity is really important. And most things move under the force of gravity. So that's here. Now, when we talk ice ages, we're talking about big chunks of time where the Earth's climate is just generally cooler than normal, but there are also fluctuations within an ice age. And we call them glacial periods and interglacial periods. And so the glacial periods, obviously, as the name implies, involve the advancement or propagation or formation of glaciers. And the interglacial period is when things warm up a little bit, not a lot, but enough that those glaciers pull back a little bit and they retreat. Now, there are two types of glaciers, and one of them is more common, obviously, than the other, which is alpine glaciation. And if you've ever been to Portland or Mount Hood, you've heard the term alpine lodge. And that just, the term means mountainous, basically. Alpine usually refers to kind of the edge of where trees are willing to grow in terms of elevation. But it generally just means mountainous, right? So we have glaciers that form on big mountains, and then we have ones that are continental and spread out a large distance. You can probably name at least one, possibly the other one. There aren't many on the planet right now. So alpine glaciers form in mountain valleys. They're typically confined, and they're very similar to rivers or streams, as I'm prone to saying, because that's the technical term. But they flow through the valley and downhill toward the ultimate base level, which is the ocean, right? And then the Titanic happens, and oh, the humanity. So alpine is mountain glaciers, and they have like ridiculous terminology because they're really cool. Here's an example from my home state of Washington, which is Mount Rainier, and Mount Rainier is super cool. And when we go back-ish to igneous and volcanic stuff, we'll talk more about why, but like Mount Rainier doesn't tend to erupt explosively or catastrophically, but it does tend to do what we sort of loosely call burping, where it will release heat, among other things. There's a lot that comes out when they burp that can melt the glaciers on Mount Rainier, which is why a lot of the cities downstream. I make finger quotes when I say that because it's not always like a stream. But a lot of the cities and towns downstream of Mount Rainier practice regular drills for the possibility, or more likelihood, eventuality, that it's going to trigger what we call a lahar, which are hugely destructive. But we'll go back to that eventually. Now, continental ice sheets sounds like a continent, right? Because that's where the term comes from. You get it, right? Because y'all are smart enough to understand this, or you wouldn't be here. Because I could be kind of annoying and weird and all those things, but if you are clever, yeah, whatever. I don't know. To be fair, I've had a little bit of the drinks, so this is kind of a science with shots, but not quite. Anyways, so continental ice sheets spread out across an entire body of land, i.e. continent. The most common examples and the only real modern examples are Antarctica and Greenland, which was deliberately named Greenland to try and trick people to live there. It's covered in ice, which is kind of cool. Here's an example, the big example, right, of Antarctica. And you can see it's broken into two sort of sections, East Antarctica and West Antarctica. There are some mountains in the way and also seawater, which salt makes ice melt or form at a lower temperature. So that's why that happens. But you can see how the ice is bigger in the middle, right? It's taller. You can see that. Yeah, that didn't work. Go back, you jerk. So East Antarctic ice sheet. Words are hard. Let me go here. That's the wrong end. So right around here, you see that that's the highest elevation. And in the west ice sheet, see it right there. Gravity takes things from a high elevation to a low elevation. So everything's going to flow out from that highest elevation. But the thing about ice is that it does a lot of damage to the rocks as it goes. So, anyways, to form glaciers, I'm throwing things tonight, you need cold, obviously, because ice doesn't form if it's toasty warm, right? Typically, that's going to mean latitude, so you're going up towards the polar regions, but it can also mean altitude. The higher up you go, the colder it gets because reasons, right? Space is cold. Let's go with that. So, like, if you're looking at 30-ish degrees latitude, you're going to be talking Himalayas or Alps. But as you get into the polar regions, that ice is going to come further and further down toward sea level. You also need precipitation. And if it's cold, that's going to take the form of snow, right? And it gets packed down smaller and smaller. And as it does, it recrystallizes. It compacts itself down. So snow is like 90% air. And, you know, every snowflake is unique-ish, I assume. We won't go into that because physics is confusing. Eventually, though, it's going to lose a lot of that air. The pretty decorative, sort of amazing structures are going to be lost, and we're going to get granular ice, which is sort of crunchy and granular, right? So it feels like grains of salt or something. And it's still about 50% air, but as it continues to compact down, it loses that air. And we call it firn, which is one of my favorite geological terms. But anyways, once we get down to glacial ice, you have about 20% air as bubbles. And those air bubbles become super important when it comes to looking back in time. They represent a kind of snapshot of what the atmosphere was like at the time that snow landed. So we can count it like tree rings in a lot of glaciers and go back in time to see what was going on in the atmosphere. We have sort of two zones, but the glacier is always moving, even if it's not getting bigger, like it says on the slide, right? So we have two different sections. Okay, we actually have three different sections, but two major sections. So we call them accumulation, which means to increase or gather up. So that's where snow is falling, it's compacting down, and it's under the force of gravity pushing down the hill. Once we hit a point where it's warm enough to cause more melting, among other things, then we're getting accumulation. We call that the zone of ablation. When you and it says, let me get rid of that. There we go. So accumulation is less than ablation. We're going to be in the ablation zone. If they're equal, it's sort of the boundary, which can be wider than just a line. And if accumulation is greater than ablation, we're adding more material there. And so, it's pushing down. It's very much, almost entirely, like a conveyor belt, where it's always pushing down. New material is being added at the top and pushing the existing material downhill because gravity is a thing. You can often identify the transition between these two zones just by looking. And I'll give you a second to kind of take a look at this picture and see if you can figure out what the difference is. Okay, it's been 2 seconds, so we'll go on. Accumulation zones tend to be white because the snow falling on top of them is fresh. There's no melting, so that's all you see. But as you get into the ablation, or sometimes it's called wastage zone, the ice and snow are starting to melt, and so all of the other crap that's inside of the glacier, because glaciers are immensely erosive, they tend to pull a lot of stuff out of the ground, out of the soil, out of the rocks. And as the ice and snow melts, and if you've lived in an area where snowfall is regular in the winter and gone to a parking lot of a store, like especially like a mall or a strip mall, you'll notice that they plow all the snow up into a big pile in one location, typically further out. But as the snow melts, it turns brown and then black. And that's because all the gravel and dirt and ick, garbage, whatever. And as a kid, I used to play on these things. So, they won't kill you, but it's kind of gross when you think about it. All of that stuff starts to be exposed as the ice and snow melt around it. And so as you get further and further into the wastage zone, and here's our boundary right about there, right? You can see that it becomes darker and darker because the gravel and the chunks of rock and the dirt and just anything that isn't water functionally is going to go away, and you're going to be left with the water is going to go away, and you're going to be left with all that other stuff. And it becomes darker and darker. And I love seeing things like this because it's so telling. I mean, this, and you can almost see it in this picture, is the boundary between two big glaciers coming together. And there's a term for that. We'll get there. I love the vocabulary of glaciers. So in the zone of ablation or wastage, you can get 4 different types of loss. Obviously, and this is the most common and most recognizable, is melting. The temperature is higher than the freezing temperature for that water, and so it melts and you get water, right? But the other big one is calving, and that's where big chunks of ice break off and form icebergs, right? And those can sink ships like the Titanic. The other 2 methods of loss of material towards the foot of the glacier are going to be called sublimation, which is this thing where a solid turns into a gas. And that's not the normal way of things forming. To gases usually has to go through the liquid stage, but ice especially is prone to sublimation and will just go straight from solid to gas under the right circumstances, which are annoyingly complicated and mathy. So we're not going to go there. The other option is wind literally pulling chunks of ice off and throwing them out to wherever, probably the ocean. We call that wind erosion because it can do that, right? So here is in Antarctica. This is another thing that happened about a decade ago, but I have very vivid memories of this, where we have a very large chunk of ice just falling off. And you can see it happening, right? That chunk of ice right here is doing a calving where it's just falling off into the water. It's also called calving if it happens on land, but it has different impacts than sinking the Titanic, right? And incidentally, that's a lot of ice. So, onward. Here's an image of one of the, I think this is the one that happened more recently, that was referenced early on in this video, but like they just fall off in big chunks. And it can be very sudden and very catastrophic if the temperature changes are fast enough and dramatic enough, which obviously. But going back to being a more focused on glaciers conversation, as glaciers move over the land, they tend to pull or remove or erode lots of material and carry it down to the end of the glacier, because again, it's a conveyor belt. Anything it picks up higher up, it's going to pull down toward the end. We have two different types of movement in glaciers, and it really depends on temperature and saline content. But you know, in a wet glacier, which is a little bit warmer, we see water underneath that allows the glacier to move quite a bit faster and do significantly less erosion. It's kind of sliding down the water slide. And we call this process basal slip because, as my SEDSTRAT instructor professor taught us a couple decades ago, geology is the triumph of terminology over common sense. So we like our terminology, right? We love vocab. Basal slip, right? If we have a colder, drier glacier, the slip occurs between the different grains, and it's much slower. And this illustration is great. Again, fair use. Don't sue me. Whatever. I don't. So it's more of a deformation, and there's a lot more drag along the edges. So this is called plastic flow. Kind of like really cold silly putty. If you have your hands on that, you gotta really give it some push, but it will eventually move. Now, our colder, more plastic glaciers are going to pick up a lot more sediment. They're going to be a lot more erosive, and they're going to be more dramatic. And the final results of these guys, using that term as a general neutral term because I'm old, and I'm working on me always, right? We all are, but some of us more than others. So these big things, big boys, I'm going to call them big boys, tend to rip a lot out of the ground because they're so cold. And when you're looking, well, with any glacier situation, but especially with this slower, colder plastic movement, most of the motion is taking place as far away from the contact with the substrate. So here's a contact, right? Here's a contact. and then this line really along the sides. So where it's touching rocks, it's going to move much more slowly. So the middle of the glacier is going to move more quickly because there's nothing holding on to it. It's basically not dragging against the side. It's only dragging against other ice, which is more fluid. So the fastest movement is always going to be top center, and the slowest movement is going to be along the sides and bottom where it's contacting the bed, there's that term, or substrate. Love these guys, by the way, ASU. I've done a lot of research down there with them. And they have some fantastic faculty and fantastic facilities, so lots of fun. Glacial movement is like slower than your fingernails move. No, wait, that's faster. Sorry. It's a little bit faster than your fingernails grow. It's about 75 meters a year. If we're going to multiply that by 3, so like 225 feet a year. Not a lot, but significant compared to plate tectonics, right? They move, they just don't move super duper fast. They also, especially the alpine glaciers, but all of them tend to reshape everything that they come across. So here is our before picture where we have these nice, soft, rounded mountain profiles. The valleys are shaped by the streams flowing through them, so they tend to be more V-shaped. And again, when I get to that point, I'll post streams and talk about that. But I'm really interested in talking about glaciers and climate change because it's such a big deal right now. And I want to be able to say, just watch the video on climate change, right? So, much more rounded, much more like rocks falling under gravity as opposed to being ripped away and pushed downhill. So we call these V-shaped valleys. Glaciers form a different kind of valley, which we call U-shaped valleys. And one of the reasons for that, obviously, is because if you have, a valley and there's a single stream running down it, that stream is the only thing eroding. And it's going to keep eroding, and it's going to keep eroding. And this stuff is only going to fall down when the slope becomes too steep for whatever it's made of. Whereas if you have a valley like this and you have it completely full of glacial ice, all the places are going to get eroded as opposed to just the place where the river is touching, because the ice is touching everywhere. So it tends to create these valleys that are shaped more like that. That's what we call U-shape. Let's look at that. So they tend to grind and also do this thing called plucking, because, and if you've ever gone ice skating, you've experienced this phenomenon. When you press on ice with enough force, you melt it and create kind of a thin layer of water underneath whatever is pressing down on it. And so when you're ice skating, those blades under your feet are causing a thin film of melt in the ice that you can then glide across. I love ice skating. I also love skiing, possibly more, although with my ankle it's sort of problematic, but I'm going to get back to it eventually. The reverse of that is that when you have ice that's being unpressurized, being pulled away, it tends to freeze harder. And when it does that, it grabs onto the bedrock and rips out chunks. And so that and anything else that's ground up underneath the glacier, because these are large, meters to kilometers thick piles of ice that are grinding across the ground. And so it's going to bring material downstream or downflow as it goes. And that produces, again, I said, this sort of U-shaped valley. Okay, that's just ignore you. More like this, right? And you can really see this. Here it is. Here's your U shape in that valley. More like that, but still. Because it's eroding on both the sides and the bottom, as opposed to just along the bottom where our streams happen. And so that can result in some really dramatic and specific topography. And these are some of the terminologies we're going to use. The terms horn, cirque, arête, hanging valley, and they almost always have waterfalls in them, and then this U-shaped valley. Those are our big vocabulary when we're talking about alpine glaciers. Let's move on. We can see evidence of this in the past, and this is what geologists generally do, is we look at the rocks and then we go, okay, how did this happen? And then we tell the story of how it happens. When glaciers move across ice, they tend to make these scratches in the ice because they're carrying bunches of gravel and rocks and other crud. And so they will pull across and just scrape it like a big comb, right? And what's really cool about these is if you find them and you run your hand over them one direction and then go back the other, you will feel a difference. They are smoother going down motion than they are going up motion. So these can tell us exactly how they moved. And then there are also these, we're going to look at that in a little more detail here in a moment. But we'll go back to that. And then there are even, so these are called glacial striations or stria because they are little teeny tiny lines, right? You can see them. They're just little bitty lines. They're very fine. So that's striation or stria. But we can also get grooves. And this is what happens when a glacier is moving through with like big chunks of rock in it and they just gouge into the bedrock. This is around Kootenai, not Kootenai Falls. This is the dam up in, I want to say Boundary County, Idaho, or it might be Bonners County, Idaho. And you can walk across this bridge and see this. It's so awesome. Glacial grooves, words are hard, are these bigger, they're like stria, but they're bigger, and then you can see the stria inside of these grooves where it's just been really aggressively carved out. Here is what I was talking about when we see those marks right here. Those guys. These are called plucking structures. And they can tell you, you can see it's a very straight line here, right? I took this picture, by the way. This is up around Bonners Ferry, Idaho. You can see that there's sort of a slope coming up here, right? And this is because the glacier was moving this way and it grabbed a chunk of rock, this chunk of rock, obviously, and ripped it out straight off. And so they tend to form these shapes like this. And the reason that you can feel the difference going downstream and upstream is because there are microscopically sections like this all throughout this mess, right? But this just happened to be one of the bigger ones and thought it was kind of nifty. They create a lot of features, and they are typically in alpine glaciation erosional features. When we look at continental glaciation, we see depositional features. I'll get to it. But here you can see the iconic, and this really is iconic, U-shaped valley, right? Big broad valley. If we were going to look at something that was only carved by a stream, it would probably look more along that lines. So here it is again, big, broad, wide swales, U-shaped valley. Gorgeous. Go to Glacier International Peace Park. If you ever get the chance, it is amazing, right? And then we have Kid Rock, right? The rock, and Ice Cube in the middle. So we have a glacial valley here. Rock, ice, rock. There we go. It works, right? We also see a lot of other structures. And this is where our hanging valleys come from. The bigger the glacier, the deeper it's going to carve. The smaller glaciers don't dig down as far. And I'll get to these terms like cirque and tributary and stuff. We'll get there, right? When the glaciers go away, when the Ice Age ends, we're left with all these features. And the big one here is this hanging valley thing, right? You can see them. There's 3 of them in this image. Because the biggest one cut down a lot deeper, it sort of truncates or cuts, there's that word, truncated. It cuts off the other valleys and leaves these very straight, sheer cliffs. And above those cliffs, you're going to see these additional U-shaped valleys that seem like they're just hanging out at the top of the cliff. And they produce amazing waterfalls, right? Other terms are cirque. So there's the definition. It is a steep wall-shaped bowl, right here, right? Steep walled bowl-shaped, sorry, words are hard, we've covered this, valley at the head of a glacier. And that's kind of the important part. It's at the head of a glacier. There we go. So they're at the top, right where the glacier is really depositing. And then as it comes down, it's going to dig that out deeper and deeper, and so they end up being kind of bowlish. And they will often form lakes in them. When the glacier retreats, and we call these a tarn, so that's the lake in a cirque, because again, vocabulary, triumph over terminology, we like our terms. We also, okay, I've already talked about this. I'm not going to but the hanging valleys form because, again, I should really reorder these slides. I'm not going to, but I should. They tend to, cut off these smaller or tributary glaciers, and they become hanging valleys. So they're these valleys that are basically hanging out way above, and then the cliff is there and waterfalls ensue. It's beautiful. So here's an example at Glacier Park. Again, one of my favorite places on the planet. It is absolutely gorgeous. And there's really good barbecue in the towns around it, incidentally. Very good barbecue. So there's our hanging valley. It's got a glacier that's coming down instead of a waterfall. Another term that we use is a horn. Very English compared to the rest of it, which is very French. But a horn, and the most common, example of this is the Matterhorn in Switzerland. These are these pyramidal peaks, these very sharp, spiky peaks. And you can really see it in the Matterhorn right here, right? It is sharp, almost like a needle. It is super sharp. And they are formed by 3 or more glaciers coming down. Typically, it only goes up to 4, but as a rule, 3 or more glaciers that surround it, and then you get this peak that doesn't have the erosion, and so it just sticks up. If you only have 2 glaciers coming down on either side, you get these jagged, sort of knife-like, or knife edge is the term that we like to use for it, sort of spines that go between each glacier, and we call this an arête. And an arête it basically means a stop in French. It means stop. And so they're the stop between 2 different glaciers as they erode down. Another thing that we see in alpine glaciation is a fjord. And these are basically just a glacial valley that, as sea level rose back up and the glaciers melted, became flooded with seawater. And they are gorgeous. I mean, just amazing. The surface of the glacier is actually really complex. They're not typically just like a flat sheet of ice. Because they're in motion, they form these cracks or fissures, here's one, right? Here's one, and then here's a whole bunch of little bitty ones. We call them crevasses. I know, it's how it's pronounced, crevasse. Not crevice, crevasse, because French is a language. And they form by brittle behavior, and we'll go back and talk brittle versus ductile eventually. Basically, it breaks instead of bends when it goes over things that might be more resistant, or when it spreads out more. Anytime you see a change in the shape and dimensions and rate of movement, you're gonna get cracks or crevasses. If you like sort of fantasy-esque / historical fiction, the Clan of the Cave Bears books by Jean Ahl, who is fantastic but a little bit raunchy. Actually, in the 4th book, I want to say, talks a lot about crossing a glacier and the crevasses. So if you like to learn that way, check out the Clan of the Cave Bear books. They are fantastic, if, like I said, a little bit raunchy. Now, we're going to transition from erosional to depositional features. So now we're talking deposits versus ripping things out of the ground. And these form toward the end of an alpine glacier or in continental glaciation towards the ends. The big thing is till. And that's just a mix of rocks and dirt and whatever the heck else the glacier pulled out of the ground and then smushed underneath it, or in front of it, or on the sides. It's basically any sediment that has been moved and deposited by glacial ice. And as a rule, it tends to be really poorly sorted, or well graded if you're an engineer. So it's got a fine grain matrix and then lots of big chunks, because the glacier tends to do both. Now, when we're talking till, there are, because terminology over common sense, lots of vocabulary around this. If you've read The Wheel of Time, these will make you giggle. If you haven't, you should read them. They're amazing. Fantasy. I love fantasy and science fiction. I write science fiction, right? So these are called moraines, which is the name of a character in The Wheel of Time, so I always laugh at that. And they're named dependent on where they are relative to the ice. So when you're at the terminus or end of the glacier, you're going to get a thing called end moraines. I'm going to add that. Oh, it's right there. Derp. There it is. So end moraines are basically all of the heaps of sediment that were deposited by that conveyor belt coming down and dumping its load. I'm rolling my eyes at myself. At its nose, wherever that nose happens to be. And because glaciers are constantly, as climate adjusts or changes, they're moving back, they're moving forwards, you can get banks of moraines coming along like that. The one that is the furthest out, this guy right here, is called a terminal moraine, because it's as far as the glacier went, or has gone, I guess. And everything past the terminal moraine is called outwash. And this is where a lot of deposition is taking place as the melt and loss from the glacier spills out onto the plain. It's called a plain if it's outside of the mountains, right? So onto that plain there, and we'll get to that. There are also these things called recessional moraines, which are the end moraines that aren't terminal. I mean, that's the most obvious definition, or the most reasonable definition of the term, I guess. Recessional means moving backwards. So they tend to be, you can see them here, right? These ones that are sort of stepping back. So those are our recessional end moraines. They're both. They're recessional moraines, but they're also end moraines, because at one point, or even currently in this case right here, they are where the glacier ends, or where it's finally dropping its last little bits, where it's giving its last hurrah. If we go further up the glacier, we're going to find a couple of others. Lateral moraines and medial moraines. So our lateral moraines are the ones that are right along the edge. Right here. There we go. There are our lovely laterals. They run laterally to the glacier. But when two glaciers meet, as is happening here, they merge. And they end up going down not the middle, but like down through, cutting across and delineating the two glaciers that have merged. And in this case, you can see here, we have a lateral moraine here, which means that this is Glacier 1, this is Glacier 2. But then if we come over here, we've got 1, 2, 3. So we've got 3, 4, 5, 6 different glaciers merging together in this image. When they merge, these two lateral moraines become a medial moraine, or median moraine. I'll use both terms, intermixed. It doesn't really matter to me. So those just mark how many additional glaciers have merged together. So see. Again, till it's a random mixture of rock debris in a fine-grained matrix. Here we go. Some of these slides really are not in optimal order, but that's how they work. It's a long story. So here, you can really see it. Here's our lateral. Here's our lateral. These two merge and become medial. Here's another one. And here you can see lots of little medials that aren't really defined, but they tell us that a lot of really small glaciers came together to form this section. Whereas here, we're not seeing that, right? There's nothing there. Here we see, I think those are actually crevasses in this, but here you can see 1, 2 glaciers that have formed that particular situation. Now, once we get outside of the accumulation zone and get into the ablation zone, we get into a lot more deposition. So we're seeing the glaciers drop material as opposed to ripping it out of the ground. So after our end or terminal moraine, then we get deposition. But we also get a little bit of deposition underneath. We call that a ground moraine, or just till is what I typically say. But, if you're a glaciologist, you might use the term ground moraine, because that's all the material that's been packed down underneath in the ablation zone. So here is how that typically happens when we're talking alpine glaciation, where we have, here's a nice lateral moraine, right here, but then they become medial, right, as they come into the middle. So as these glaciers hit a more gentle slope, which is to say lowlands or foothills, they tend to, instead of continuing to flow forwards, puddle, right? I mean, you can see it here, obvious, right? They form sort of a puddle of ice. And they're still pushing forwards. You're still going to get your moraines. Here's our end moraine, which may be terminal. It's hard to, in this case, I suspect it's not terminal. You're going to be like way down that direction. So how does the end moraine form? That's really kind of cool. We'll go to streams eventually, but in this case, we're looking at sediments that are poorly sorted and a lot of water coming down all at once. And so that's going to give you our braided streams. And you can really, I love this picture, right? You can see all of these channels are breaking off and sort of intertwining. And if you've ever braided hair, that's kind of what it's like. So an outwash plain is where we are at the base of a glacier. It's dumping all of its water, and all of the sediment that that water carried eventually gets deposited, and it starts carving these just interweaving, sort of beautiful stream channels. And so when you see something that looks like this, where you've got these big, large islands, for lack of a better word, islets, I don't know, and lots of streams that are branching off and then coming back together, good chance you're looking at glacial outwash. But regardless, it's a braided stream coming out of a glacier in this case. Now, one of the other things, we're going to come back to this sort of multiple times, when we're looking at glaciers advancing versus retreating, as we move into more glacial periods, obviously the temperature drops, and so our glaciers are accumulating more and losing less, so they advance. But as the temperature rises, they melt and waste more compared to the amount that's being put in at the top. Because if you have, 5 minus 1, we're going to get 4. But if you have the same 5 as input, but 3 as the output, you're only going to get 2. So it's going to start backing up as that final number here decreases. And we've seen this happen. So Mount Gould, this is part of the glacier park, Grinnell Glacier, you can see here it came all the way down into the valley. Now, however, in 1981, special year for me, I was born in 1981, so that tells you how old my butt is. It's moved back a considerable amount. If we go forward 17 years, you can see, compare these two, right? It has stepped back. In 2006, and I suspect now in 2024 it's worse, it's almost not reaching this particular pond, but just combined to this upper section. Let's move on to continental glaciation, which has some of my favorite vocabulary. So these happen when you have mostly high altitude, Greenland, Iceland, as examples, or you're in a glacial period. And the area of thickest ice is going to be the center of the dome. And the ice is going to move out from this spot in all directions, right? You can see it here. There we go. Our most recent big ice age, oh God, I am not wording tonight. The last ice age ended about 11,000 years ago. I can't remember what it was called now. I'm sort of dumb. But we had 2 ice sheets on North America. I'm not sure about the rest of the world. One of these days I'll figure that out. But today I'm just talking North America. You can see there's a boundary between the Cordilleran and the Laurentide. Spell that out. I think that's it. It'll come back up in the slides here very shortly. The Cordilleran's kind of its own kettle of fish, but the Laurentide sort of obviously has a center right there. And all of the ice moved out from there. That's not right. Let's go that way. Right, it's moving out. I don't know for sure, but that might be why Hudson Bay exists. Don't quote me on that, though. But you can see, so we have the deposition zone, and this is where, like it says underneath my marks, the zone of scouring. This is where a lot of just grinding and mucking about takes place. Here is where we get the most erosion, because this is where we're sort of at that boundary between wastage and accumulation, and so you get freeze-thaw cycles, and that tends to be more erosive. Once you get down below that, though, in terms of elevation or latitude, you're going to get a lot of deposition, because all of the everything, rocks, dirt, whatever the heck it goes across, is going to be deposited down here. And the Cordilleran's kind of funny because it actually does have multiple erosion zones and scouring zones, as well as deposition. But anybody guess what differentiates the two? A for the Dave, you said the Rocky Mountains. We call continental ice sheet features Kame and Kettle topography. We'll get to why that is. But it's because there's a lot of deposition and calving. We tend to get a lot of these very soft hillocks, but they tend to have a sort of directionality to them. And you can actually see that in this image, right? There's sort of we call it a fabric that tends to move like that, right? So everything is moving from the top left to the bottom right. Because we have that giant conveyor belt that is the glacier, it's pulling everything from the top of the glacier and then carrying it on down to just plop it down at the front or underneath, depending on circumstances. As this monster here goes back, i.e. temperature rises, so it's losing more from the end that is coming down than is coming down at the beginning, it's gonna march back. We use that term. And it creates some really cool features as it does that are dependent on the direction of motion. So here we have, like I said before, our outwash plain, which is at the tip or at the end of our terminal moraine. There's that term. Here we have an end moraine that could be also called a recessional moraine, right? Because that's one of our lines that's marching back that represents the recession or retreat of the glacier. These areas all tend to be prone to lots of lakes and marshes because the till or ground moraine underneath the glacier is so compacted that water doesn't easily transfer through it into the underlying strata. And that's why Minnesota is the land of 1,000 lakes, in part because the water doesn't go down, but also because of these guys, the kettle lakes. We'll get to them. But our big terms are highlighted in the biggest red circles, so drumlins, eskers, kettle lakes. Those are the three biggest, but not all of the terms in relation to continental glaciation. Again, we've talked moraines before. These are end recessional terminal and deposit situations. They're made up of that stuff called till, which is really poorly sorted. You got a fine-grained matrix, lots of big chunks. Nothing is particularly rounded. It's kind of a dog's breakfast, i.e. a mess. They're the same moraines as found in alpine glaciation. They just happen to be more depositional, and sometimes they happen in weirder shapes. The glaciers when you get into the zone of ablation, the glaciers become even more complicated than when you were in the accumulation zone because the melting starts to carve stuff out, and so you get these like tubes that go down into the glacier. I mean, the water is going to go where the water is going to go. Until it gets into the subsurface of the planet, as opposed to the ice, it's carrying a lot of sediment and it's going to deposit that sediment. You'll get these really amazing, awesome things where you have a stream that's draining out under the base of the glacier and it carves a tunnel, but it's also, and you can see it here, depositing a lot of sediment under the glacier. Here's another example of that. It's so cool. They can be really long and they look so cool, but they form these things called eskers. And eskers are basically an inverse of a stream. The stream has gone under the glacier, but the ground underneath it is frozen solid. And so the sediments and the water can't dig down, so instead the sediments pile up. And so you get these, like I said, inverse of a river. And we define them as long, sinuous, or snake-like ridges formed by the sediments deposited under a glacier by a stream. And so here you can see it, right? That's stream shape. Here's another one coming through here. They're basically rivers under glaciers that couldn't dig down, so they dug up. They're really neat looking. These are mostly in northern Washington. Here's another one in Kame's National Landmark in Washington. Here's the ridge of it, and it sort of curves off over that direction. Another thing we can get underneath glaciers are called drumlins. And these, and you can really see it here, are these sort of teardrop shaped long ridges, and they tend to taper towards the back end as the ice just sort of crushes that material up into these shapes and then drags it out. And so these can tell us, it's really kind of nifty, the direction of motion of the glacier. The steeper side is where it's being just sort of packed down, and then it's drug out to the shallow side. So this is our direction of glacial movement, and that's what's really helpful about drumlins, besides, I love the name, is that you can tell the direction of glacial movement. We have a lot of them in Washington. Minnesota's going to have them anywhere in the like Midwest to the north. You're going to find these guys. And, you know, here is our steep side, and here is our shallow side here. So we know our glacier here was moving that direction. Kind of nifty. Kettle Lakes, land of 1,000 lakes. This is why. As the glacier moves back and as it calves on land, it's dropping these gigantic chunks of ice. And that's got weight to it. And so when they hit, smash, smush, they form little craters in the ground. And they can displace some of the till, potentially, but they're also packing everything down underneath them. And so they fill with water and become little bitty lakes. Or, okay, I say little bitty. I grew up with very large lakes. We call them kettle lakes. And that's where the term Kame and kettle, or kettle and Kame and kettle, or kettle and Kame. Try saying it 5 times fast. Right? And here's, you know, obvious example, little bitty kettle lakes, all the freak over the place to breed mosquitoes. Good times. Another thing that we see are called erratics. And I, as a younger kid, like 12-ish, thought this term was the funniest frickin' term ever. Glacial erratices, or glacial erratics. These are rocks that are, because glaciers are slow moving, right? And erratic means, you know, going off all over the place unpredictably. But these are, glacial erratics or erratices are rocks that are wildly different from their surroundings that have been deposited by a glacier. So here are some other examples. They can be really far from their point of origin, and they can be gigantic, right? I mean, there's this sign, right? And you imagine a normal person stands about here. So you imagine this is a pretty sizable chunk of rock. These are carried by the ice. The ice rips them out of the ground, and then they tend to float in water a lot of times inside of that chunk of ice way downhill. So here's Juneau, Alaska, the Mendenhall Glacier. Here's an erratic that's going to go down to here, and eventually the ice will melt, and then that rock will drop wherever that happens to be. Here's one on the Colville Indian Reservation. Again, Washington, that's where I live. Also, frickin' gorgeous, right? I mean, amazing. This is my picture because I've actually been to this. It's called the Oregon's Geological Glacial Lattice. And this is in roughly Newberg, Oregon, which is like an hour from the beach. Go there, it's gorgeous, right? There's a pear tree growing like right over there. This is a chunk of granite that was plucked out in northeastern Montana and carried in ice as the water flowed down toward the ocean and eventually dropped right here. And it's just wild. Here's another example, Jaeger Rock. They can tell us how far the ice sheet pushed, and they can tell us how far the outwash or glacial flooding went as well. Again, here's our outwash plain. It creates a braided stream because everything's being deposited. These typically are right at the end of a glacier. Now, another thing that's generated by glaciers, and this picture was taken very close to where I live on the boundary between Washington and Idaho, between Pullman and Moscow. Loess. It's pronounced L-U-S-S. Loess. Not lust. Loess. Is defined as fine-grained silt. Glacially derived wind-blown silt. That's the term I usually use. And it's this level right here. So when a glacier goes down and it grinds up the rocks and it forms a relatively fine powder, the wind picks it up, carries it to wherever. The Palouse is an area that is famous for this particular sediment because it is so fertile. It has a lot of nutrients, a lot of ions, basically, that are in it that really contribute to great plant growth. And so we are actually known as the lentil capital of the world. We grow more lentils here and chickpeas in our neck of the woods than anywhere else on the planet. But we also grow a lot of wheat. That's very common. Here it is. Glacially derived wind-blown silt. And so it just blankets everything underneath it and is typically, at least in our neck of the woods, really great for growing stuff. Here's where we are. So here's the Palouse. I may have spelled that wrong on the previous slide. Use this spelling, that's more correct. And we had this situation in the western half of the United States where the Cordilleran ice sheet came down and blocked, and also up here in Montana, rivers. Ice makes a really crappy dam. I bet you can figure out why if you think really hard about it. What does ice do in water? You nailed it. It floats. And so when the water behind these big glacial dams built up enough, it would lift the dam up. And as it lifted it up, because these bad boys are brittle, they shattered. And then all the water that was stored in these lakes, especially Lake Missoula, we'll get there. We call them the Brett's floods. And also Lake Columbia, which was part of what is now the Spokane River, because it was also blocked by the Cordilleran and everything was forced to come this way instead of going along the normal path. This didn't fail as readily as the one up here. Kind of obviously because that's much bigger. But when these ice dams fail, all of the water that they've been holding, basically the entire lake, and if you're familiar with the region, you'll know that this is Lake Coeur d'Alene, right? And it is a beast all of it in itself, right? And you have Lake Pandora up there. Here's what it looked like during the Pleistocene. There's the correct spelling of Laurentide if I spelled it incorrectly, and the Cordilleran. Here's our Rocky Mountains coming down here, dividing the two sections. But here, Lake Missoula, and it had a very small ice dam right there. And then here's Lake Columbia or the Spokane area. The Lake Bonneville also plays a pretty big role in our neck of the woods, but for different reasons. When this ice dam was not thick enough to hold back the water, it all came splurping down all of this area. Less this area, more up here. Here's Lake Bonneville, which was another glacial lake. It eventually drained when it eroded through a sedimentary layer up here and drained down, and then all that was left was here, the Great Salt Lake, which is still a pretty massive body of water, right? I used to live there when I was little bitty. So the Bonneville Lake drained out here, and then Missoula came down here. And what's really cool is if you go to Lewiston, Idaho / Clarkston, Washington, which is actually more up here, you can actually see where these two lakes met as they outwashed. There are deposits from both in some quarries in Lewiston, which are super cool, right? Better example of Missoula. So here's the city of Missoula, and this is Lake Missoula in Montana. And here's our ice dam, again, smaller than the one that came down and blocked Columbia Lake. But eventually this ice dam gave, and all this water, roughly the size of one of the Great Lakes like Superior over in the Midwest, drained out over the course of roughly a week. That's a lot of water moving really fast. And so it came down through this part, which is the lowlands, and scoured through it and formed a braided stream shape. And you can really see it like right here and right there. Here's a little island. If you drive through this area, which I've done a bajillion times, it's so stark. These just islands in the middle of it, and you can really tell where the Missoula flood came through. Although it wasn't until we started having more satellite images that we actually understood what was going on here. And the Brett's floods were named after Brett's, who was the first person to identify this stuff. So, I mean, the water just came crashing and screaming down, right? The Wallula Gap is this very narrow section of the Columbia River, and because it's so narrow, the water ponded here. And we see a lot of erratics deposited right along the what was the shoreline of glacial Lake Wallula. It went through Portland area, and if we were living during that time, here's our very tallest building in Portland, and it would just stick up above the water. Most everything else was underwater. Here's Mount Hood, beautiful, right? Lots of water. Now, when there are a lot of glaciers, that means the water has come out of the ocean and is being stored on land. And as a result, when there is increased glaciation, we see sea level drop. And on the west coast of North America, well, the sort of west coast of North America, this portion of it, we see a pretty significant, so here's 10 kilometers, so there is probably about 12. We see, and so if we're talking miles, we're looking around 5 miles. That's a long way out, right? The shoreline moved a significant amount all the way out. And what's cool is if you look at the underwater images, you can actually see the Columbia River in there. Here's another river, right? I don't know what one that is, but it's pretty cool. So now we're going to go into glaciers and global warming. How are these two related? Weather is something we experience every day, right? It is the day-to-day variations in temperature, in humidity, in precipitation, in wind, like all of the things that make up weather, right? Climate is a little bit different, and this is a long-term average. So, and we tend to classify climates depending on locations, and amount of solar radiation. But climates, the big part of this is long term. We're talking decades to centuries long. Because you got to remember, in terms of geology, 4.5 million years ago was like yesterday. I work in rocks that are roughly 12 to 15 million years old, which is Cenozoic. So for me, that's like stupid early, because Cenozoic started at 65 million years ago, and the preceding section, the Mesozoic, i.e. time of the dinosaurs, started 255 million years ago. So I'm used to thinking in these big chunks of time, and so like 100 years is not that long. That's nothing. I'm terrible at remembering anniversaries and birthdays, incidentally. So what happens during glaciation? We have these reservoirs of water on the planet, and we'll talk about streams eventually, but the largest amount of water on the planet, I think sort of obviously, is stored in the oceans. But glaciers, here we go, and polar ice make up a pretty significant amount. And then you've got, groundwater and the other sections, lakes and rivers, atmosphere, and the biosphere, which is actually kind of significant. But this is the main dynamic we're concerned about tonight. Today, whatever. I don't know, I just work here. Is the glacier versus ocean. So when you take water out of the ocean, when you deposit water here in the glaciers, it's coming from typically evaporation out of the ocean. A little bit from lakes and streams, but this is our big Bertha in terms of sources. So as this goes up, this is going to go down, and sea level's going to drop. At about 18,000 years ago, during the peak of the last ice age, we saw an 85 meters. 8 times 3 is 24, so like 240 feet-ish. That's rough calculations. We saw a humongous change. Massive in sea level. So much so that I think most people have heard of this land bridge right here. When North America and Eurasia were connected on dry land. And this is where they think probably humans moved from all of this stuff over to here. There was a lot of other life that was able to go back and forth, but the big mover in this situation was us. Homo sapiens sapien. Right? So that's how humans got to North and South America, and then they obviously, from North America migrated down. There are other locations here, we've got that connection. We've got much bigger space in New Zealand. I don't remember what that island set is. I know this is the Philippines and Indonesia and that sort of stuff. Eurasia, here's India, right? But this was all one land. There weren't islands there, it was all one land. So, it was big when this happened. In our continental glaciation, again, this ended about 11,000 years ago. These guys started to march back, leave lots of deposition. And sea level rose as the ice melted, because that water has to go somewhere. It's going to go into the ocean. Now, so we've established when temperatures rise, ice melts, and that water goes into the ocean. Ocean levels rise. If we have lots of glaciation, the water is going from the ocean to the glaciers and being stored on land. Ocean levels drop. Why? Why does this happen? Why do we have periods of glaciation and periods of warming? What causes this? Well, this is a great video, by the way. I'll leave it here for a second so you can watch it. It talks about Hurricane Sandy, which happened, a while back, but I was teaching when it happened. It was kind of a big deal. Um, and Hurricane Sandy is one of the examples, really good examples of what happens as sea level rises a little bit, even a couple of feet can cause major problems for areas that are low-lying. Now, we have short-term and we have long-term variations. The short-term fluctuations, which is between glacial and interglacial periods, within an ice age, words. God, I am bad at this. I'm going to leave it in there, though, because it's funny. I think it's funny. These short-term fluctuations within an ice age or outside of an ice age, because we'll still see them in the non-ice age periods, are related to the amount of solar radiation that gets to us and stays. The stays is kind of important. We have sort of three features that factor into that, because physics, and I kind of want to quote Doctor Who, physics, right? I don't speak physics all that well. You'd have to ask my other half, who was kind of into that. But we have this thing called eccentricity, and it changes on about 100,000 year scale, where we go from a low eccentricity or low sort of spread to our orbit, I guess, or lack of circularness, because gravity is a bully. So when we have low eccentricity, we have a more rounded shape to our orbit. We're still accelerating here, losing velocity, and then accelerating again. But over time, it will change to a more elliptical orbit, and we call this high eccentricity. And it's going to change the amount of solar radiation that comes consistently to the planet. If we're in a situation where there's low eccentricity, we get a more consistent amount of solar radiation on the regular. Here, though, we see high, but extreme lows over here. And so that can cause increases in glaciers. Another term is called the tilt of the Earth's axis of rotation. Because our planet doesn't sit straight on line with the orbital plane, right, which would be here, but is at a slight angle, we get seasons. I mean, that's how we get seasons. So when the north is pointing away, that's winter for us, and the south gets summer. And when we're going the other direction, like this, then it's summer, winter. I'm not writing clearly, it's okay. And this can vary on about a 41,000 year time scale between about 21.5 to 24.5, but it makes a big difference. The other thing that is really impactful in our short-term fluctuation is called precession, which is a term that I love because it's weird. I don't know. But precession is how steady the Earth's axis is. If it's always pointing one direction and not going back and forth, it has low precession. But over time, especially as the spin of the magnetic core swaps, we'll see it sort of go back and forth. And if you have a top and you watch, as it gets towards its end, it starts wobbling around all over the place. That's precession. But because the Earth's magnetic core will eventually restabilize, this will stop for a while and then go back to wobbling back and forth. And this is a 23,000 year time span, which is, roughly half of what we saw in the tilt, which is roughly half of what we saw in eccentricity. This results in what we call the Milankovitch cycles, which are, so here you see the eccentricity as that goes up. We see a little bit more of a tendency to glaciation. When it's low, not much glaciation is occurring. Our precession here, as it hits its peak, we get glaciers. As it drops, we lose them. With our tilt, low tilt, glaciers, higher tilt they vanish. As we go down, we get more glaciers. So, and again, it's just about the amount of solar radiation or heat that is making it to the planet. Just the amount of heat that's getting to us from the sun. But our long-term causes tend to be ones that keep the heat, that trap the heat. The big Bertha of the whole thing is plate tectonics. Because when we have continents on the poles, we get a lot of land ice that builds up as opposed to melting into the oceans. And so we move into our glacial or our ice ages. And then that Milankovitch cycle controls the glaciation versus interglacial periods. When we don't have the polar land, we tend to stay interglacial the whole time, so we don't have ice ages. But when we have these continents, they get the buildup of ice on land. When we don't, the ice can't build up, so we don't get that continental glaciation. We just have alpine glaciation, and that allows the oceans to better circulate the water, to circulate the heat. And then our climate can also, our atmosphere can also impact this in a very big way just by trapping heat. We'll get to it. Here we go. So other factors that can lead to glacial versus interglacial, ice age versus not, is a lot of this is just how the heat gets trapped, other than this bad boy. So volcanoes can release sulfur gas, water, chlorine, fluorine, and carbon dioxide, all of which have their impacts. Chlorine, fluorine, we won't worry too much about. They're more local, but sulfur, carbon dioxide, and water are all problem children. Sulfur causes the atmosphere to cool rather dramatically, but it's short-lived. Carbon dioxide and water cause the atmosphere to warm up, and they tend to be a little bit longer lived. Our reflectivity of the Earth's surface is largely dominated by that whole ice versus ocean water conversation. And when that happens, then we have problems with the Earth's thermohaline or heat and salt currents in the ocean for reasons. So here we have the thermohaline current, and what we notice is we get the most solar radiation at 0 degrees latitude, which is to say the equator. The further up we go, the less radiation we get, so the less evaporation takes place. If we're losing a bunch of water here, it has to flow down from the poles where we're not losing as much to the equator. And as it does that, it tends to be cold water, so it's going to travel along the bottom of the ocean. But when it gets to the equator, it starts to warm up and it rises. And this is how how heat is transferred around the planet predominantly, is through these ocean currents carrying the heat, basically, up to the northern areas. And what's really nifty is if you look here, we have this current kind of bumps into the bottom of the UK. And this is the reason that it is warm here enough that coconuts grow. It's also the reason most of this is habitable, because all that heat's being carried up there and keeping it warmer in that neck of the woods. Because if you look at it here, we have glaciers, and this is roughly, a latitude line. So we look at this through a lot of different ways, but we are actually pretty adept at figuring this crap out. One of the ways we can do this back to about 10,000 years is called dendrochronology. which is looking at tree rings. If you know about tree rings, you know that each line represents a year of growth. But there are two different sections, right? There is the lighter color and the darker color. And the darker color is basically winter when growth is slow, and the lighter color represents summer when the growth is faster. And we can count them back based on archaeological finds and other deposits that go back that amount of time. We can actually track them back to about 10,000 years, which is kind of crazy. But they're an analog for temperature, because the warmer it is, the faster they're going to grow, so the wider these lines are. The colder it is, the slower they're going to grow, so they become smaller, and we can calculate that out. Okay, I'm talking about people who actually work in this field. Another thing that we can look at, remember, we have like 20% gas in glacial ice, and these are gases that were trapped when that snow fell and have been kept there mostly unchanged. And because of that, we can look at a lot of the gases that are in the atmosphere. We can also pick our sulfur gases out from that. And then we can also look at variations in isotopes, but that's more complicated. This goes back some 10,000 years, further in some cases. So we can look at exactly what the atmosphere was like during time periods that we can then go back to the tree lines and say, okay, it was warmer here and we're seeing this gas concentration. So this gas concentration probably contributes to warming. And we do that 1,000 times to get data that is reliable. We can also look at isotopes, like I said. Oxygen is the big bad boy in this conversation. Oxygen comes in a couple of different isotopes, but the big ones are 16 and 18. Really what you have to know about those is 16 is smaller, right? And because it's smaller, it's lighter. And so when it is cold, 16 is more likely to evaporate than 18. And so because it evaporates out of the ocean and then ends up in our ice, when it is colder, we see more oxygen 18 in the ice itself. I think I said that wrong. Oxygen 16 is more common when it's cold. As it warms up, this 18 gets enough energy to go off, and we can find more oxygen 18 on land and less of it trapped at the bottom of the ocean in what we call a calcareous ooze, which is calcite and aragonite, but they're basically functionally the same thing, that all get deposited on the bottom of the ocean. So we can match the stuff going on at the bottom of the ocean, which is trapping the calcite, with where the ice is being trapped on land, and kind of say, okay, so during these times it was colder, during these times it was warmer, just from that. It's kind of cool. So there are lots of ways we can track how things have changed over time with regards to ice and ice age and glaciation. And so this is kind of the timeline that we've picked out from that over time. We know that cooling began about 50 million years ago, about 15 million years after the dinosaurs showed up, but reached kind of a peak at 1.8 million years. We see our glacial episodes when the Laurentide and Cordilleran, I almost said that wrong, which is embarrassing, were at their peaks during the Wisconsin glacial episode, which peaked at about 20 million years ago. And then at about 12 million years ago, we entered a major interglacial that sort of transferred into a non-glacial. I mean, we're not really in an ice age these days. But in terms of plate tectonics, we kind of are. That happened at about 12,000 years ago. And here's how it syncs up with our Milankovitch cycles. Again, when we have the three parts, the tilt, precession, and eccentricity, when they come together like Goldilocks and they're just right, we get big glacial advances and retreats. And we've already talked quite a bit about this, but as the glaciers increase, because the water is being transferred from the ocean onto the mountains, especially onto the land, we see the ocean level drop as the glaciers build. As the glaciers melt, sea level rises. Very straightforward. We see a lot of changes in the landscape, the Great Lakes, like I've talked about with that Kame and Kettle topography, the channeled scablands, and then anything in the alpine glaciation where you're seeing those arêtes and cirques and horns and tarns and paternoster lakes, which is basically a bunch of little lakes coming down from the cirque. Now, the greenhouse effect. So, let me go back to this. We've established, I think fairly well, that this is a thing, right? So if we have a warmer situation, the ocean level is going to rise. If we have a colder situation, it's going to drop. Now we talk climate gases or greenhouse gases. The three big bad nasties of the conversation are CO2 or carbon dioxide, carbon, methane, also a carbon molecule but different, and water. As these are added to the atmosphere, they function as kind of a really nice thermal blanket, like really well insulated. They're an insulation. And so what happens is they trap the heat and prevent it from bouncing back out the way that it usually does. This is a fantastic video. I can't show it here, but you can totally look it up. The mean old greenhouse gases who beat up the sun rays and the heat, the sun rays, and trap them on the planet. It's a mess. Carbon dioxide is probably of the three kind of the least offensive, but it's also the most voluminous. So it has the biggest impact. Methane is really big, but it only comes into play in certain situations, i.e. cow farts, because they produce methane. But when we look back at the geologic timescale, and here's old, here's now, we see that about 70 million years ago, 65 million years ago, what happened at 65 million years ago? The death of the dinosaurs. We'll get back to that in another slide. We saw a tremendous drop in the carbon dioxide rating, or carbon dioxide concentration on the planet. And this period right before the transition is called the Carboniferous, because there were these just massive swamps that really pulled a lot of carbon dioxide out of the air. And it may have contributed to the event that wiped out the dinosaurs, but there were other factors involved. It was sort of a double punch. So we look at this over time, geologically speaking, and it has gone down a lot, the concentration of carbon dioxide in the atmosphere. And that's because plants photosynthesize, so they eat up the carbon dioxide and spit out oxygen, which we breathe. But more recently, so here's modern times. Here's 1 billion years ago. Here's our, I want to say that's our 65 million year range. So before that, we had a lot of carbon dioxide in the atmosphere, and our climate was very different. But after that, it's been really steady state for 65 million years until now. And now you'll see that, and as we zoom in, you can see it is shooting up exponentially. And that's because we're taking several million years, several million years worth of carbon that has been stored in the planet, especially in the form of coal, but also in the term of oil and gas, and releasing all of that carbon dioxide back into the atmosphere. So all of the carbon that was stored up from here to here by photosynthesis and other methods, but mostly photosynthesis, when we burn coal, we're just pumping that back out into the atmosphere. So we're taking millions of years of carbon dioxide and spitting it out in a century, which, like I've said, is really short time for the geology. So when we look at this graph, it's really quite obvious. Here's our Industrial Revolution, and kersh, it's really shooting up very quickly. And by 2100 AD, so in about 75 years, it may be back in, okay, so that's 700, here's 1,000, so we're looking at pre-dinosaur time. That's not good, because it's a big change and it's very fast. The planet needs more time than that to adjust. No, it's not. That's crap. Humans are contributing to the changes in our atmosphere. We are pumping out ridiculous amounts of carbon dioxide. As the carbon dioxide causes warming, then it causes additional evaporation in the ocean. And the water joins the carbon dioxide, little buggers, in the atmosphere and causes even more warming. If that goes on long enough, then we see melting of the tundra and then the methane hydrate burps, and it gets even worse. And then we get into sort of this greenhouse versus hothouse climate, which is kind of a mess. The climate change that we are recording is clearly significant. Anybody who has lived through the past, 5 years, knows that every year has been the hottest year on record, and it keeps going up. We keep seeing more catastrophic storms. We see storms where they shouldn't frickin' happen, like in the Pacific last year. I had a very good friend of mine and colleague in some regards who was super concerned. They lived in the middle of Oregon, and there was a hurricane that could potentially impact them in the middle of Oregon. Hurricanes don't happen on that coast, but they did, and they're going to keep happening because we're effing around, right? Another YouTube video that's very helpful, a couple of them actually. I love YouTube videos when they're good. There are a lot of garbage YouTube videos, but the ones that I've recommended here, are typically pretty awesome and accurate. So CO2 is not a humongous amount of our atmosphere, but it has an enormous impact to the greenhouse effect. So again, 0.03. If we were talking blood alcohol content, we would be at roughly half the legal limit. I'm probably above that right now, if we're being honest. So 0.04, because we're rounding, can produce anywhere between 9 and 26% of the greenhouse effect. Methane is a much smaller percentage, only because there's not much of it in the atmosphere. You'll notice that water vapor, though, is a big contributor. And again, as the carbon dioxide level goes up, we're going to get more warming, which is going to contribute to more evaporation of the oceans, which produces more water vapor in the atmosphere. And that just keeps compounding the problem. It's kind of a runaway thing. So, global warming versus climate change. And actually, we don't use the term global warming much anymore, scientifically speaking. We really talk more about climate change, because it's really the oceans that are warming, although you'll notice, again, hottest summer on record keeps happening because the overall planet is warming up. But if we saw all the glaciers on Earth, which unlikely, but we would see a 250-foot rise. We divide that by, I can't divide that by 3 off the top of my head, but it's significant. Anyways, we see a humongous rise. One of the things I want to point out is goodbye Florida. Literally, Florida is underwater. New York City is underwater. Washington, D.C. is under the ocean. We lose a lot. Although, if you're on the west coast, like just south of Portland, you're going to get oceanfront property. Isn't that going to be nice? This is the slide I like to end on, incidentally. Of these 2 slides I like to end on. Kilimanjaro, which is the mountain that is the furthest south that has glaciers. It is in Africa. It is almost equatorial. And in 2005, it had a decent number of glaciers. It's a pretty tall mountain. And, here you can see the names. I'm not going to try and pronounce them. I don't speak any of the languages in that province. But you can see we have a northern ice field here. We have a southern ice field here. 2004. Ready? 2012. This was 12 years ago. The southern ice field has gone down to here. Remember, it was all in here. The crater had it. The northern field was like this. There is a new rift that formed in 2012, and most of it is gone. Gone. Let's go back and forth a couple of times. If you had any doubts that the overall climate of the planet is warming, just look at these 2 pictures. 8 years. That's all the difference in these pictures. 8 years to almost completely lose the entire glaciation of Kilimanjaro. It's obvious that something is changing. And it is going to continue causing all sorts of disruptions and problems, and new locations are going to become unlivable, and that's not going to change. It's not great. It is something we really need to work on and address. We need to be moving to electric vehicles. I wish I could afford one. But, and that's really hard. We have to do something. Everybody in the industrialized world needs to be acting, because everybody on this entire planet of Earth is going to be impacted by this. Changes in the atmosphere, changes in the climate impact crop growth, they impact the temperature you live in, they impact the amount of water available, it impacts everything in your life. Really. This is a thing. I'm an expert. I have papers published. Davis et al., 2012. You can read it. We can impact the climate, and these gases make huge differences. We have to do something. Climate change caused by humans is a thing. I can't say that enough. It's a thing. And we need to change the way we behave, because the planet has shown over the course of geologic time, look at the death of the dinosaurs, that no matter what happens, she's gonna recover. Earth will find a way, life will find a way, but that does not mean that humanity will last. The planet is full of the history of life that has died out. We have about 255 million years of that. Since the Cambrian explosion, when life really started to show itself in the fossil record, and there was stuff before that, back to not back to 4.6 billion years, but I want to say roughly 2 billion years. I think I have a fossil that's that old of a stromatolite. Life will recover. The Earth will recover, but that does not mean it will recover with us in it. So if you want to get down to the absolute core of it, caring about climate change is really caring about the future of humanity, of us. It's important. Please take it seriously. That's all I have for you tonight. I can't believe I made it this long. Have a nice day, night, whatever. Take climate change seriously. Look at what you can do to reduce your impact. It's not just up to the individuals. And I cannot stress this enough. Individuals do not have a huge impact. It is largely corporations, power generation, industrial farming. That's where a lot of the greenhouse gases are coming from. But individuals can impact that through their buying choices. So shop local. Because transportation is the biggest cost in terms of carbon. Shop local and try to reduce what you put out into the environment. Try and reduce how much water you use, because all of these things will help. You can make a difference. And every single person that makes a difference adds to the benefits. Even a tapestry that seems impossibly large, if you make a couple stitches, you're still making progress. We have to work on this. All right, Series Klarissa is going to bed. I love you all. Take care.